titration since we're middle to end of it, so we could kind of stay on pace and not break up the lecture so much here. So we were looking at this example here towards the end there of lecture, and let us sort of talk about it here. So in this particular case, we are taking acetic acid and we're reacting it with sodium hydroxide. And sorry, a little construction and stuff going on next door. So we're taking some acetic acid and reacting it with some sodium hydroxide. Again, up in the burette is the sodium hydroxide, and in the beaker, the flask, whatever it may be, is our acetic acid. So we're adding the base to the acid. So obviously we're doing the titration, so we do need to do an ice table. And we would have our reaction of acetic acid plus our sodium hydroxide going to give us our sodium acetate. Oops, no. And our water, H2O. All right. So obviously, like we've been talking about, this is a titration, so we're constantly adding volume. So we do want to do these guys in terms of moles. So we want to figure out the moles of everybody that we're starting with. So we got 25 milliliters of 0.1 molar acetic acid. So that would get us 0.0025 moles. For our sodium hydroxide, we have 27.5 milliliters. So 27.5 milliliters of 0.1 molar sodium hydroxide, which would get us 0.00275 moles, and 0 this guy. So again, if we're not sure where we are at, as we've been talking about in this titration, it's good to have an idea as to where you're at. So we're definitely started with our acetic acid. We have our sodium hydroxide is what we're adding. When we do a comparison of the moles of what we're adding to the moles that we are starting with, we see that we are adding more moles of base than what we started with. And what that should tell you is you are after the equivalence point in that particular case. That also should tell you then that this guy here, our acetic acid, would then become the limiting reagent, and we would use that as our change. So it would be minus 0.0025 plus 0.0025. That means when we reach equilibrium, we got nothing of the acetic acid left. We got 0.00025 moles of that guy and 0.0025 moles of our sodium acetate left over. Any questions on the ice table up to that point? At this point, as we talked about, pretty good practice that once you do that initial ice table in moles, you then should go back and really convert it into molarity. Otherwise, you can get into some trouble if you don't do that. So our total volume at this point, we started with 25 milliliters in the flask. We added 27.5. That gets us 52.5 milliliters. So we will divide these guys by 0.0525 liters. And that will convert us back into molarity. And if we do that, 0.00025 divided by 0.0525 gives us 0.00476 molar, and 0.0025 divided by 0.0525, 0.0476 molar. Again, always a good idea to look at your table, see what you got going on. So here we have sodium hydroxide left over. We have sodium acetate left over. Obviously, we don't do anything with the water as it doesn't do much. So we are after the equivalence point, and we know hopefully in this type of titration that after the equivalence point, as we've talked about, we will be left with a salt that will go through hydrolysis, but we will also be left with a strong base, which is what we got going on here. So again, we have a strong base. We have a basic salt, but out of the two, and as we talked about in this point in the titration, this is where we ignore the contribution of the salt and look at just the strong base. So in this case, that would give us our hydroxide concentration. And we then could get the pOH, which would be minus the log of 0.00476. Gives us a pOH of 2.32. Now, if for some reason you thought this was the pH at this point, and it does happen because sometimes people write the equation wrong and they think this is the H plus concentration, and you have a pH of 2.32, that should not make sense to you based on where you are in this titration. Since you are past the equivalence point, since you are dumping sodium hydroxide in there, which is a base, you would expect this pH to be basic. So again, these are the things you want to think about as you're going through these problems. Make sure everything makes sense. You're not thinking about things sort of incorrectly. That means we do need to subtract 14 there from that number. And if we subtract 14 from our 2.32, looks like we end up with a pH of 11.68, which is basic. It is sort of what we would expect to occur at this point in the titration, again, because we're pretty much just dropping bases down into that solution, or dropping a lot of strong base into that solution. Question on that part of the calculation there. And we could kind of just see on our example here how we did. So we were at 27.5, which is in this ballpark. And at 11.38, it does fit in between those numbers. So at least that's good. That sort of makes sense. So this type of titration that we're looking at, as you can hopefully see, is, although it may appear to be similar to the first titration we talked about of a strong acid, strong base, there really is 4 distinct sort of areas. Before you start, which is a Ka problem. Once you start titrating before the equivalence point, it's a buffer problem. At the equivalence point, it's a hydrolysis problem. And past the equivalence point, it's a figure out the concentration of strong base type problem. So super important to understand where you are, because like I said, before you even pick up your pencil or pen or crayon, whatever you're using to write with, you should have a pretty good idea what type of problem you should be doing and where you should end up in terms of the pH. Makes it so much easier than just jumping in and trying to figure it out as you go along. Again, a lot of people make a lot of errors sort of doing it that way. Any questions on this specific type of titration here? All right, then that brings us to the last type of titration we're going to talk about. And that is a titration of a strong acid with a weak base. Now, this titration is a little bit different than the previous two. It's hair different in terms of what it looks like, the titration curve. Not so much in terms of calculations, but it's a little bit different in terms of the setup. So in this particular setup, what is happening is up in the burette is actually the acid. So we have the hydrochloric acid up on top. On the bottom, we are adding it to our weak base, which in this example is NH3, which is a weak base. That is why when we look at this titration curve, it looks backwards, if you will. We are starting up high in pH, and that's because we are starting with a base in the beaker, and we are adding acid, which means we expect the pH to start to drop. Still sort of that S shape, but it starts higher, kind of a backwards S, if you will. So it's very similar in terms of its shape to what we saw here, but again, it's sort of flipped upside down because we're starting at a high pH and ending at a low pH, as opposed to what we were just talking about where we started at a lower pH and ended at a higher pH. So let us talk about these different parts. So there's really the same sort of 4 areas on this titration curve. And by the way, you see a similar drop in pH to the equivalence point and a similar drop afterwards. Again, we see more of a drop here because we are adding acid as we come to the equivalence point. So before we start the titration, right there, and before we add any HCl, if we think about what we have in the beaker, our flask, we essentially have just a weak base. Again, because it's a weak base and it's a base, we're starting out at a higher pH in this case. And what that means is in terms of your calculation at that point, because you only have a weak base before you start the titration, like our NH3 here, it really is just a KB type problem, which means because it's a weak base, you cannot go right into the POH or anything like that. You do need to have your ice table. And remember, as we talked about, when we have a base, probably a good idea to have the water there, going to accept the H plus there, going to give us NH4 plus and OH minus here. Now, again, because you have not added any hydrochloric acid in this case, you can do this ice table in molarity. So you would do your molarity. These guys would be zeros. These guys would be X's in this case. Again, typically, if you're using molarity, you're using X's. Molarity minus X, X, and X. Again, because this is a base, we would go into our KB expression. We would solve for X. X, as we can see from the table here, is the hydroxide concentration. That will again allow you to first get the POH and then to the pH by subtracting 14. So again, this is very similar to the titration curve that we just saw, our titration that we just talked about. The only difference is in the previous one, we were starting with a weak acid, which made it a Ka problem. Here we are starting with a weak base, which makes it a Kb type problem. Any questions on what's happening here at the opening start of this titration? Again, because this is a base, that is why we see the titration curve starting high in terms of its pH. Again, because we're adding acid, so we should be lowering the pH as we continue through this titration. Okay, so let's take a look then at what happens in this type of titration as we head through starting our titration here. When we start adding that HCl to before the equivalence point, sort of in that second region, or 20 region, I suppose, that second region that we have seen before. So once we start adding our HCl here, we are going to get the reaction that's going to occur, which is up there on top, but we'll take a look at it closer here. So at point 2 in this sort of titration, once we start the titration, again, we're going to get that reaction of our hydrochloric acid, in this case, plus our ammonia, which is the weak base, going to get us NH4, and I'll split it apart. So this is NH4 plus Cl minus. You could, like on that first one, keep it together as NH4Cl, however you want to kind of do it. But I'll break it up so we can kind of see what we have going on in terms of all the pieces here. Again, can't keep it together as ammonium chloride. So again here, because we're doing this, we're obviously adding volume. We're going to do our ice table here in moles. And I'm going to use my same starting number again. I just made it up. So in this case, we're actually starting with the base in the beaker. So we're going to start with 4 moles of our base. So this is what we're starting with. This is what we're adding. And if we are again before the equivalence point, we should have not added enough acid in this case to have neutralized all of the base that was there. So our moles of our acid should be less. So we'll go with 2 moles here, 0 and 0. Now, again, because we're before the equivalence point, what we are adding, which is the HCl in this case, is going to be the limiting reagent. It's going to get used up in this case. So our change would be 2 moles all the way across. And when we get to equilibrium, none of the HCl there, 2 moles of this guy, 2 moles of this guy, and 2 moles of this guy. Again, like we've been doing, we will convert everybody back into molarity using our total volume. And now we really want to kind of think about what we have left at this point and what we have left that's going to perhaps affect the pH. So we have NH3 left over, as we can see from our table. We have NH4 plus left over, as we can see from our table. And we have Cl minus left over from our table. So let us first look at Cl minus. Cl minus came from HCl. HCl is a strong acid, which means Cl minus will be relatively weak. And as we know from a lot of experience, hopefully at this point, Cl minus is a neutral salt. So the presence of that Cl minus is really not going to affect anything. So really what we have left over is NH3 and NH4 plus. So we basically have NH3 left over and NH4 plus. Hopefully at this point you can recognize that these two things are related to each other. That is a weak base and its conjugate acid, right? So weak base and its conjugate acid. That is also known as a buffer. So at this point in this type of titration, you are going to be left with a buffer. And you then could go into our Henderson-Hasselbach equation at this point. You want to make sure you get the base up on top, the acid on the bottom, and you want to make sure that you are using the pKa value here. You probably will be given a Kb value at this point. You probably would be given the Kb value of NH3, which is okay because you could get the pKb from that if you like, and you then could go the pKa would equal 14 minus the pKb. Or again, you could use Kw as Ka, Kb, and convert it and get to the pKa value as well. So there's a few different ways you could get to the pKa value if you were not given it. You just want to make sure, obviously, that you are using your pKa version here, base over acid. Again, this is going to be a basic buffer. Some people would say, since you probably have the pKb, this might be a good place where you could use what we talked about before, the kind of basic version of this Henderson-Hasselbach equation to get the pOH and then subtract 14 to get to the pH. So again, you have a variety of sort of options in this sort of place here, but I would probably stick with our Henderson-Hasselbach, probably the better way of doing it. Third option is you could also do an ice table if you wanted to. And again, the ice table, a couple of different ways you could do it. You could do your NH4 plus, making your H3O plus and your NH3. And again, initially here, both of these guys, we want some numbers happening there. This, by the way, would be H2O. This would be donating, and that's how we get there. So again, to keep it simple, probably I would stick, if you recognize it as a buffer, with the Henderson-Hasselbach equation, but you do want to, again, make sure that you're not just sticking in the pKb value thinking it's the pKa value. So this is very much like the last titration as well. Once you start this type of titration, anywhere from opening bell, when you drop those HCl in there, all the way up to that equivalence point, you again will have a buffer region in this area. So you'll have a buffer type region in here. And again, going to require at least one ice table, and then the Henderson-Hasselbach are your choice at that point. Question on this part of the titration curve here. So again, as we are progressing, we are coming down in pH, and as I said, kind of exactly like what we saw in the other one. Instead of having a rise in pH because we're coming down, we get usually a drop in pH to the equivalence point, and then we get another drop past the equivalence point, also pretty vertical coming into the equivalence point here. So let's talk about what happens in my big circle here exactly at the equivalence point. We'll call it number 3 like we've been doing. So on the third part here of this curve, when we reach the equivalence point, at the equivalence point, we will have our reaction, which again is our HCl, our NH3, and again, you do get ammonium chloride, but again, I'm just going to break it up so we can see all the parts. You can keep it together if you like. All right, so again here we're going to use moles, and we're starting with this guy here. So we're going to use our 4 moles. And again, because we're at the equivalence point and we understand what that means, we understand that that means the moles of acid should equal the moles of base. So we understand that we should have exactly 4 moles of HCl in this case, because again, that's what it means when we reach the equivalence point. 0 and 0. Again, here you can't really choose the wrong number as there's only one number involved. So -4, plus 4 moles, and plus 4 moles on this side. That is going to zero us out in terms of our HCl and our ammonia, which is good because, again, that is your definition of equivalence point. We will end up with, again, 4 moles of this guy, 4 moles of this guy. We're going to convert it into molarity by dividing by the total volume. And now what we're left with is basically a salt. Although I broke it apart, we're basically left with ammonium chloride, which again is a salt. And as we talked about in the previous step, again, our chloride coming from hydrochloric acid going to be neutral. So really not going to affect the pH. So that really does leave us one salt or part of the salt to consider, which is our NH4+. Now, our NH4+ does come from a weak base, which is ammonia, NH3. And because it comes from a weak base, like we talked about with our salt, it will go through hydrolysis. So here, much like the last one, after we produce that NH4+, it will continue to react. So it's going to continue to react in a hydrolysis reaction, and we will need a second reaction and a second ice table. So the NH4 plus will react with the water. And again here, if you're not sure how it's going to react, we think about it like a step before. So since our NH3 is a weak base, that means that its partner should be a conjugate acid, which means when it reacts with water here, it's going to react as an acid would, which means it's going to donate its H plus over. When it donates its H plus over, that gives you NH3 where it came from, and that gives you H3O plus here. And again, as we've talked about, by writing these reactions correctly is really important, because by just seeing that H3O plus on the product side here in our correctly written equation, we know several things. We know before we even finish this calculation, it should be acidic. We also know that we should be using a Ka value here. Again, in this titration, you probably would have been given the Kb value. So it is going to require you to use that Kw relationship perhaps to get the Ka value. So again, as I've emphasized a lot, it's super important to be able to write these reactions correctly, because it just sets up your calculation part really well. If you're struggling in terms of writing these reactions and you're not really sure what you're writing, you're going to find yourself probably struggling a lot in the calculation part. And again, you don't want to just kind of go autopilot here. You want to make sure you get these things down correctly. And then not only write them correctly, you do want to think about what you are looking at. What does it tell you? Because it does tell you a lot of information. So what we're going to do here is an initial ice table here. We are going to use our value from the equilibrium line as our initial value here for molarity. Also, why it's important at this point after the first table to convert these guys back into molarity. Again, as we talked about, technically speaking, in the last step, if you choose to use the Henderson-Hasselbach equation, it will come out okay with moles. But if you're going to do a hydrolysis problem here, you probably need molarity to get the right answer, unless you know really what you're doing. But you probably do need molarity to get it right. So again, that's why when I say it's important to convert back to molarity after that first table, it's a good idea, because it puts you in the right units for the rest of the calculations that you need to do. And really, you don't have to worry about units. So again, these are the things you want to watch out for as you're doing these problems. We're going to finish this up like normal. So since we got some molarity, we're going to use some X's here. And we'll have our initial minus X, X, and X. And again, by recognizing our H3O plus, we will know that we need to put this into a Ka expression and use the Ka value here. That again is going to allow us to solve for X. And as we can see from our ice table here, X is equal to the H3O plus, which is the H plus. And that will allow you to get to your pH value at that point. So very similar to the last titration here, when we reach the equivalence point, you will need one ice table to figure out the salt that you're left over, and you will always end up with a salt that is acidic and will produce H3O plus, which means you need a second ice table, which is the hydrolysis reaction, and again, should yield you that acidic pH that you would expect. Question on that there.
Oh, at the beginning of the step, how do we know that Cl minus is like neutral, or is that something we just know?
It's something you should know. We talked about it in relationship to salts earlier on in this chapter, I think. So it has to do with that salt part, and it's that relationship that if the salt, a salt really comes from probably an acid or a base. So the salt itself is really from a combination of an acid and base. And if that part of the salt, like Cl minus, comes from something that's strong, it's going to be relatively weak and will not go through hydrolysis. So since Cl minus comes from HCl, which is a strong acid, Cl minus is considered to be a relatively weak base. And what that means in terms of it is it won't react with water. Now, NH4 plus, like we have here, comes from NH3, and NH3 is a weak base, which means the NH4 plus is a relatively strong conjugate acid here, and it will go through hydrolysis reaction. So it's that relationship that we talked about mainly when we talked about hydrolysis and salts, I think earlier on in this chapter. So that's how we kind of know that. So basically anything that it comes from group 1 or 2 on the periodic table, which is why we ignored like sodium earlier, is a neutral salt. Anything that comes from a strong acid or strong base is essentially a neutral salt. Other questions on that? Okay. So at this point in this titration, again, you're always going to yield that salt that will go through hydrolysis, and it will produce that acidic solution because it's basically going to produce that H3O plus. And that's what we see if we look at this graph here at the equivalence point. In this particular example, it's like 5.28. 5.28 is acidic. And that's what we would expect in a titration between a strong acid and a weak base. Other questions on that there? Okay, so what this is going to leave us is the rest of the titration curve here. So again, maybe your indicator has changed colors at this point. It doesn't stop you. You're just going to open it up and let it flow in. But different in this case is, again, remembering that we are adding acid. So that's why we're seeing our pH come down. So at this point, once we go past the equivalence point, we're essentially just dumping in a bunch of acid into that solution. So at this point, past the equivalence point, all the way through, let's talk about what happens at that point. Oops, come back. So on that fourth step, once we're after the equivalence point, we are still having our same reaction, which HCl in this particular example, NH3. Again, I'll keep these separated so we can kind of look at them separate. But again, nothing wrong with actually keeping the ammonium chloride together. Initially here, again, we're going to start with our made up 4 moles. Here we're adding, again, our HCl to it. So since we are past the equivalence point, we would expect now, because we're just dumping in a bunch of acid into that solution, we would expect to have more moles of what we're adding than what we started. So again, I'll just use my 6 number that I made up, and we would have 0 and 0 at this point. The consequence of being past the equivalence point is we get a change, and now our ammonia becomes the limiting reagent, and our HCl is like the excess reagent. We got plenty of it. So what that means is, again, you can't get a negative concentration, so we're going to have a -4 here all the way across, +4. That's going to give us 2 moles of this guy, nothing of this guy, 4 moles and 4 moles. Again, very good practice, highly recommended. You should just do it. Convert these guys back to molarity after that first table. And now again, we got several things perhaps with numbers here if you did it like I just did there. But we want to kind of look and see what we got going. So we have some HCl left over at this point. We have some ammonium left over at this point. We have some chloride left over at this point. So let's just start right to left. So since we were just talking about chloride, for everything we just talked about, It is still, again, basically a salt that came from a strong acid, which means basically what that is a neutral salt. So you don't really have to worry about its contribution to the pH. We have our NH4 plus, like we saw previous step, will go through hydrolysis. So this guy will go through hydrolysis. It will be acidic, right? It will produce H3O plus. So, it's going to act as an acid. We also have HCl, which is a strong acid. So really what we have left, again, is very similar to what we had in the previous titration. What we have left at this point is two acids. We have a strong acid in the sense of HCl, and we have sort of a weaker acid, if you will, in the sense of ammonium. So the same idea applies here. Is once that HCl goes into the solution, so when you open up the burette and you just dump that HCl into the beaker, it essentially is just going to hit that solution and break apart into H plus and Cl minus. It is going to end up being the major contributor to H plus in that solution, because again, our NH4 plus, it's got to go find a water. It's got to do a little reaction to produce some H3O plus. So in comparison of these two at this point in the titration, again, we're going to ignore the contribution of the salt at this point, because again, the major contributor here is going to be the very strong acid of hydrochloric acid. So since this would be our major contributor at this point, and it's a strong acid, that probably will be your H plus concentration, which then will allow you to get to your pH. So it is very similar to the last titration, except in the last titration, we're adding base, and here we're adding acid, right? So that's why, again, the strong acid is the major contributor. So it does require, once you go past the equivalence point in this type of titration, to do an ice table in moles and figure out really how much of your strong acid you have left over, which will allow you to get to your H plus and your pH. Question on that calculation? And that's what we see when, again, we look at our titration curve here. Again, we do see, and that's why we see when we go past the equivalence point, because we're just dumping that acid in, we get a sudden rush of H plus, and that's what causes that big drop in pH in this case. And again, at some point, it sort of levels out. That H plus concentration, it sort of hits a sort of maximum and will sort of level out in terms of the pH. That's also why, by the way, if you remember the other titration, as we're going up, there's that jump to the pH and then that jump after the equivalence point. And again, because really past the equivalence point, you're just dumping in a bunch of base. So you get that big jump that occurs, that sort of happens at that point. Question on any of those sort of four parts? Again, just to review the four parts of this type of titration, different but similar to the previous titration. At the beginning of the titration, before you add any acid in this case, you will have just a weak base. So you need to do a KB problem like we did earlier on in this chapter. After you start the titration, all the way up to the equivalence point, it requires at least one ice table. You will be left with a buffer. In this case, the buffer will be basic, and you could go into the Henderson-Hasselbach equation after that. At the equivalence point in this type of titration, you will have two ice tables that you need to do. First ice table will leave you with just a salt, and it will be an acidic salt. The second ice table would be a hydrolysis reaction where you will produce H3O plus and why you get a acidic pH at that point. And the fourth part here requires one ice table like we just talked about, The purpose of that ice table is to get the concentration of the strong acid that's left over. And then you could go into the pH equation. Any questions on any parts of that titration curve, the previous titration curves, any titration curves? So basically, 3 different types of titrations we talked about: strong acid, strong base, different calculations kind of involved in there, a weak acid and strong base, and a strong acid and weak base titration. Any questions on any of that?
Yeah. So can you go over like which kinds of like which points in the titration we use moles versus molarity?
You pretty much should use moles whenever the titration has started. So as soon as you drop that first drop of whatever it may be, base or acid, as soon as you've added, 0.1 of a milliliter of it, you should use moles in that very first table. And when we talk about moles, really sort of in this titration calculations, we're really talking about sort of that first table. So in that first table, moles should always be used as soon as that titration starts. So as soon as you add whatever you're adding, either the acid or the base, as soon as you've added 1 drop of it, you should do an ice table and you should use moles. The time where you don't need to use moles, or you could use molarity in that first ice table, is before you start the titration. So before you start the titration, you haven't added any acid or base to it. So you could just use the concentration of the acid or base that you started with and do either a Ka problem or a Kb problem. So it is only when you have started the titration, which means you've started adding volume, that you need to do that first table in moles. And when you do that first table in moles, once you finish that first table, just convert them back to molarity using the total volume. And then you'll be fine for the rest of the calculations you have to do. So it's really sort of that first table needs to be in moles, and you need to do that whenever you've added even 1 drop, technically, of either the acid or base to it. Other questions on that? All right, or questions on titrations? Okay, a couple other things, just talk about some of these things here. You may not be given how much volume, for example, that you need to reach, say, the equivalence point. Some problems may just say, hey, what is the pH at the equivalence point? So you do need to do sometimes some stoichiometry to figure it out. If it's a 1-to-1 relationship between the acid and base, you could use like M1V1 equals M2V2, and you can figure out the volume you would need to reach the equivalence point. There's several different ways you could kind of figure those things out. You could do a basic stoichiometry problem and those type of things. So, you could kind of do those things. If you're using the molarity, if the molarity of the acid and base in a titration is exactly the same, and it is the exact same molarity, and it's a 1-to-1 relationship between them, you would need the exact same amount to reach the equivalent point as to what you started. So what I mean is, for example, in like this titration here that we did, in this example, we had 0.1 molar acetic acid, and we were titrating it with 0.1 molar sodium hydroxide. The molarity of both the acetic acid and the sodium hydroxide were the same, which means if I started with 25 milliliters of my acetic acid, I would need to add 25 milliliters of my sodium hydroxide. It's a 1-to-1 relationship. You could do M1V1 equals M2V2 to figure that out. This would be M1, this would be V1, this would be M2. You could solve for V2, and you would get 25 milliliters, and that means that's the equivalence point volume. And you can see, as we talked about in this example, at 27.5, we are definitely after the equivalence point. So sometimes you do need to figure those things out. If it's not a 1-to-1 relationship, you can't use M1V1 equals M2V2. You do have to do the stoichiometry and take that into account. But that's one way you could do it. Another way you could do it is, that, when you get to here, like I did here, You know, if you're not sure, heck, you know, I started with 4 moles of this guy. I'm at the equivalence point. I should have 4 moles of this guy. So for example, if you were given that the molarity of the sodium hydroxide was 0.1 molar, you would then have the moles and the molarity. You could use molarity is moles per liter. Liters is moles divided by molarity to figure out the volume by working sort of backwards from your table to figure out the volume. Why do you need to know the volume? You need to know the volume of how much you added to do this part of it to convert things back to molarity. So that's why that's important to be able to figure out sometimes the volume to reach the equivalence point. Again, sometimes they don't tell you those things. Lastly, as well, if you have a titration problem where it is multiple parts, like it's like, what is the pH at the beginning? What's the pH, you know, after 10 milliliters is added? What is the pH, you know, you're doing a problem with a lot of steps, like what's the pH after 10 milliliters is added, 15 milliliters, 20 milliliters. So when you do these type of sort of problems, you want to think of these problems as individual problems. And what I mean by that is if you were going to do the first problem, what that means is you opened up the burette and you added 10 milliliters and closed it. And then you would do the pH. If you were then going to do the 15 milliliters, what that means is you opened up the burette, you added 15 milliliters, and you closed it. It doesn't mean you had 10 and you added 15 more for 25. So sometimes people, when they come across a problem that has multiple steps, they keep adding the volume and they get the wrong answer. So unless otherwise specified, which it usually isn't, it pretty much means at 15, you open it up and you added 15. What that would mean is you added another 5 milliliters right from that point. And same thing here, when you got to the 20, you opened it up and you added 20 milliliters exactly. So don't add the volumes if you have a titration problem that has multiple steps. Again, you want to think about them sort of as individual, open it up, shut it to that point. Question on these 3 different titrations, titration curves in general. You do need to be able to figure out the pH anywhere along a titration curve. You need to be able to know what these titration curves look like and be able to calculate the pH. Any questions on any part of that? All right, so since we're in lab and we have some time here, this is a good example. These are 4 different parts onto a titration here. So why don't we, what I'll do is why don't you guys get together, I'll open up some rooms, work on these 4, maybe until about 1-ish, and then we'll come back together and we will go over these parts just to make sure we all understand how to do this. So I'll open up some rooms, get together and work on this, and we'll come back together and we'll go through each of these parts of this titration curve to make sure, again, everybody got the right answer, everybody, you know, has an idea as to what's going on here. All right, so these are 4 different steps in this titration curve. Make sure that you find the pH for each of them, work them out. Again, use this time wisely so that you know what's going on. Okay, so let's take a look here, and hopefully it is big screen, I hope, on your side. All right. Let me know if it's like super small or something like that, but if it's okay, we will continue. All right. So let's take a look at this one here. So we are titrating here 100 milliliters of 0.1 molar nitrous acid with 0.1 molar sodium hydroxide. And we're looking for the pH at several different points along the way here in this titration. We got the initial solution after 80 milliliters of base has been added after the equivalence point, and after 105 milliliters have been added, and we have a Ka value of 4.5 times 10 to the minus 4. So this does tell us a couple of things. First off, If you're not sure, I do see a Ka value here, which would imply that our nitrous acid is a weak acid. Sodium hydroxide is a strong base. So this is a titration of a weak acid with a strong base. So it should have this sort of very badly drawn titration curve look. And again, in this case, like we talked about before, our sodium hydroxide is up in the burette. Our nitrous acid here would be up there in the bottom. All right, so let's start with A, which would be here. So hang on a sec here. All right, so part A would be here before we start the titration. So we're starting with really just our weak acid that's in there. So as we talked about before, hopefully understanding the type of titration that we're dealing with, here we have just a weak acid, so we want to approach it as just a weak acid problem to begin with. So part A here would be just a weak acid. And because we have not added any sodium hydroxide in this case, we can use the concentration that was given to us. So we're going to take our weak acid, we're going to break it apart. Not Cl minus, try that again. And the Ka value here that was given to us, which is our 4.5 to the minus 4. So again, like I said, since we have not added, we can do this in molarity here. So the concentration of the nitrous acid was 0.1 molar, 0, 0. Change would be minus X plus X plus X here. Again, really just a Ka type problem. We get here and here. Any questions on the ICE table here so far? Again, this is going to go into our Ka expression, which is our products over our reactants. That is going to give us x squared over 0.1 minus x equals 4.5 times 10 to the minus 4. You could try to assume that x is equal to 0. And if you did that, hopefully you checked it, because I think you got like 6.7%, give or take, which means it's a bad assumption in our 5% rule that we've done before. So we do need to solve it a different way, which is using the quadratic. So we're going to multiply the 0.1 on the bottom there to the other side. That's going to give us x squared equals 0.1 times 4.5 to the minus 4, going to give us 0.000045 minus 4.5 times 10 to the minus 4 x. Again, I just multiplied everything on the bottom here to the other side. We're going to bring everybody to the same side. And if we bring everybody to the same side, that's going to give us x squared plus 4.5 times 10 to the minus 4x minus 0.0000. Guess I could use some scientific notation there. Equals 0. This is going to go into our quadratic. Throw back from back way when, right? Minus b plus or minus square root of b squared minus 4ac divided by 2a. If we put some numbers in there, it gives us minus 4.5 times 10 to the minus 4 plus or minus. If you kind of get all the numbers inside the square root, you end up with I believe 0.000180. And if you take a little square root of that, hit the right number, try that again, square root, you end up with, after you take the square root of it, 0.0134. That's all going to be divided by 2. That's going to give us our 2x answers like we've done before. So minus 4.5 to the minus 4. I'm going to do the plus first. Plus 0.0134 divided by 2 gives us an x value of 0.006475. If you do the subtract, which you probably could recognize is not going to be so good for us, you will get a negative 0.006925. Obviously, we cannot have a negative because we are looking for the H plus concentration and can have a negative concentration. So our first number there should be the correct one. And that means that our X value would be 0.006475. And that would equal the H plus concentration. And that means that the pH would equal minus the log of 0.006475, meaning that we will open up our titration here with an opening pH of 2.19. Any questions on any part of that? Now, if you did the assumption and you didn't check it, you probably got an answer pretty close to that, maybe 2.18. And again, remember, it won't always be that close, but our rule again is 5%. So at 6.7, you should not make the assumption. Any questions on part A? Truthfully, I kind of messed up on some of the sig figs, I think, but in terms of the original concentration was 0.10, so that's 2 sig figs. So probably should end up with 2 decimal places when it's all said and done. So remember that concentration, how many sig figs on the concentration is how many decimal places the pH should be. So probably in this one, since we really only used the 0.10 number, that had 2 sig figs, probably should end up with 2 decimal places. I personally didn't round too much. I don't usually round it very much at the end. Technically speaking, for our X, probably the same deal. You could probably round to 2 sig figs if you really wanted to. I personally probably wouldn't round until the very end on the pH value. Other questions? Again, remember, if you kind of round a little bit here and there, you will find yourself with probably a significantly different answer at the end. So it's good to keep track, perhaps your sig figs and stuff like that. But if you're doing multiple steps in terms of calculations, you usually want to kind of hold off on sort of doing the rounding till the very end. Otherwise, especially with stuff we do that involves, for example, logs and those type of stuff, you'll find yourself perhaps significantly off of what the answer probably should be. Other questions? All right, so we're opening up this pH here, this titration with a pH of 2.19. It does make sense as well. Again, we're starting with really an acid, right? It's a weak acid, but we're starting with an acid. Our opening pH here is acidic, so that's good. That all makes sense. Again, these are the things you want to kind of think about as you sort of progress through these calculations. Okay, so coming this away to part B. Now what we want to know is if we open up our burette here and we drop in there 80 milliliters of our sodium hydroxide and we close the burette, what would we expect the pH to be? So here we're going to, let's work through that and see what we come up with. So part B is what is the pH after we've added 80 milliliters of 0.1 molar sodium hydroxide to basically 100 milliliters of our 0.1 molar nitrous acid. So obviously we are going to get a reaction that's going to occur. So the reaction is going to occur as our nitrous acid will react with our sodium hydroxide. Going to do an acid-base reaction, so we're going to produce some water and a little sodium nitrite in this particular case. Now, since we have now started the titration, we do need to do these guys in moles when we do the ice table. So we want to make sure that we are starting with the moles of each of those guys. So for our HNO2, we would take 0.1, which is 0.1 liters, times 0.1. That gives us something like 0.01 moles for our nitrous acid. For our sodium hydroxide, 0.08, which is what we're adding, times 0.1 gives us 0.008 moles. So this is what we started with over here. This is what we're adding. So again here, if you are not sure where you are in the titration, you could use these opening numbers that we just got here to help you decide exactly where you are at. So what we started with, which was in the flask or the beaker, is more moles than what we added. So because what we added is less moles than what we started with, this tells me that I am before the equivalence point. So it should tell me that I am somewhere here before the equivalence point, right, in this titration. Now, we're going to start with 0 here. In addition, because we are before the equivalence point, that means that my sodium hydroxide here is the limiting reagent. And that will also be the change that I will have. So this would be minus 0.008, minus 0.008, and plus 0.008. That means when we reach equilibrium, I will have 0.01 minus 0.008, 0.002 moles, nothing of the sodium hydroxide as it's the limiting reagent, and 0.008 moles here. Any questions on this ice table here? So again, we have started to add our sodium hydroxide. We do need to do this first ice table in moles like we discussed. And it's at this point where you should convert these numbers back to molarity. It's usually the right move, and we want to do that with our total volume at this point. Total volume is we started with 100 milliliters and we added 80 milliliters. That's a total volume of 180 milliliters that has been added at this point. So we're going to divide each of these guys by 0.18 liters. And that will get us a couple of numbers here. 0.002 divided by 0.18, going to give us 0.0111 molar. And 0.0444 molar. So now that we converted it back to molarity, we can take a look again at our ice table to try to help us figure out what is going on. We have left over at this point HNO2 and NaNO2 and HNO2 and NaNO2. Hopefully you could recognize that these two things are related to each other. That is a weak acid, and that's the salt of its conjugate base. That again is known as a buffer. So you do have a buffer left over. Now, if you understood what we've been talking about before you even did that calculation, you would know that you're in a buffer region of the titration, and you should end up with a buffer. So again, you should actually have known what you would end up with before you did the calculation based on where you are in that problem. And what that means is at this point, you have a variety of options as to the way you could solve it, but probably the easiest option would be the Henderson-Hasselbach equation, which is used for buffers. So in order to use our Henderson-Hasselbach equation, we do need to calculate the pKa value. And the pKa value is minus the log of the Ka. That in this case is minus the log of, what was that, 4.5 to the minus 4. 4.5 times 10 to the minus 4. And that gives you a pKa value of 335. So putting this into our Henderson-Hasselbach equation, 3.35 plus the log. Now the other thing that people have struggle with is base over acid. There's a lot of factors that should help you decide which one is which, but the main one should be this is nitrous acid. That is obviously not the base. So this guy here obviously has to be our base. So that means we want to go with 0.0444 divided by 0.0111. And if we do that, we end up with a pH of 3.95 at this point. Question on that? Now, we could also think about, does this make sense? Well, we opened up our titration at a pH of 2.19. We just added some base to our acid. We would expect the pH to start to rise, right? Because we were adding base to our acid. And it did rise to 3.95. It didn't go giantly risen, but we're in that buffer area where, again, we have enough acid in there to use up the base, but we did see a rise in the pH that does match what we would expect, and it's going in the right direction. Again, at this point, if you did a calculation and you ended up with a pH less than 2.19, you're definitely going in the wrong direction. So this shouldn't have happened. Any questions on part B of the calculation? Again, alternative to this, you could have done a ice table instead of the Henderson-Hasselbach. The ice table would be just like this table, but with the correct values in it on both sides. You would have a value here and a value here. All right, no questions on that. Then let us take a look at part C here of this titration. So part C of the titration here is the equivalence point. So this again is a situation where you were not given the volume to reach the equivalence point. So you can do several things to figure it out. But again, if you look at the, if you actually look at the equation that we're dealing with in this reaction, which is HNO2 plus our sodium hydroxide, gives us our H2O plus our NaNO2. And really, you can, I will show you the long calculation way of doing it. That might be helpful for you. So really, you have the volume and the molarity of the acid. So you can convert your volume of your acid into liters. You could use the molarity of the acid, which is 0.1 moles per liter of nitrous acid. Those guys will cancel. And if you stop right now, you're in moles of nitrous acid. From the equation in stoichiometry, it is a 1-to-1 relationship, which means if you do a little stoichiometry here, 1 mole of HNO2 is 1 mole of NaOH. And if you do that, you end up with 0.1 times 0.1 gives you 0.01 moles of sodium hydroxide. In terms of the sodium hydroxide, we know the concentration is 0.1 moles per liter. So we can use the moles that we just got of sodium hydroxide, and we can use the molarity of the sodium hydroxide. And in this case, we're going to divide by it. And if we do that, we will end up with 0.1 liters or 100 milliliters of sodium hydroxide is needed to use up all of the nitrous acid that's there. So in this case, we will need to add 100 milliliters of sodium hydroxide to reach the equivalence point. That is the correct way to do it, the long way to do it. But there are other ways you can figure it out really quickly. So again, as I mentioned earlier, it's a one-to-one relationship. So the concentrations of the acid and the base are the same, which means if I put in 100 milliliters, I need 100 milliliters to get there. You could also have done, because it's a one-to-one relationship, M1V1 equals M2V2, where M1 would be 0.1, 100 milliliters divided by 0.1. Those guys would cancel, and that would equal V2, which gets you there. Thirdly, you know how many moles of your acid you're starting with. You could use the moles of the acid, which is this, and figure out how many moles, the molarity of the base you would need. So again, there's multiple ways you could kind of figure out how much volume you need to get to the equivalence point. Again, probably M1V1 equals M2V2 is probably the best way. But again, you can only use that if it is a one-to-one relationship between the acid and the base. If not, your stoichiometry is going to be wrong. And really, when we do M1V1 equals M2V2, we're doing it because this part of the calculation here is 1. And it's a one-to-one relationship. Again, if it's not, then your answer would be wrong. So I would say probably 9 times out of 10, if you roll with the M1V1 equals M2V2, you'll probably be okay. But you do need to think about sort of the mole-to-mole relationship, because if it's not one-to-one, you will get the wrong answer. Any questions on that there? Okay. So now that we sort of figured out how much we need to reach the equivalence point, let's talk about what happens there when we hit that equivalence point, which is right here. Okay, so C, we're at the equivalence point. Which we just calculated is 100 milliliters of our 0.1 molar sodium hydroxide added to our 100 milliliters of our 0.1 molar nitrous acid. So obviously we're going to do our reaction here, which is HNO2 plus our sodium hydroxide, giving us our water, plus our, what we got there, NaNO2. So at this point, we are at the equivalence point. We're definitely adding volume. We want to get our moles. So 0.1 times 0.1 gives us 0.01 moles. And that's how much we're starting with of our HNO2. So now let's pretend you had no idea what I just said. You didn't think about anything that I just said in terms of the volume to reach the equivalence point. What you should know, though, is this is sort of the last way you could figure out things is I'm at the equivalence point. I know I'm starting with 0.01 moles of my nitrous acid. Because the definition of equivalence point is equal moles, without doing a calculation, I should know I need to add 0.01 moles of sodium hydroxide. And if you were at this point and you still needed to figure out how much volume, you would have the moles and you would have the molarity like we just did on that other calculation. And at this point, you would be able to figure out you need 0.1 liters of it. So again, even if you couldn't reason all that stuff we talked about previously, you should hopefully be able to reason that you need equal amounts. And then at that point, you have moles and you have the molarity of the base. You can figure out the volume that way. So again, that's another way that you could do that. Since we're here at the, excuse me, since we're here at the equivalence point, we have the same numbers in both spots, so you really can't mess this up. This should be minus 0.01, minus 0.01, and plus 0.01. This means that at equilibrium, we have none of the nitrous acid, which is what we would expect. We have none of the sodium hydroxide, which is what we would expect to happen. And we got 0.01 moles of this guy. Again, why it's important to figure out the volume to get to the equivalence point is for right here. I want to convert this back to molarity. So my total volume now is 200 milliliters. We started with 100 of the acid. We added 100 of the acid. So we would divide by 0.2 liters. And I'll just write it to the left there. That will give us 0.05 molar. Any questions on that ice table? All right, at this point, again, we could use our ice table to help us understand what is going on. And we are left with a salt. And this salt here, we need to decide, will it do anything? It is sodium and nitrite. Sodium, again, will not. Nitrite will, because it, again, comes from a weak acid. So it comes from a weak acid, which means my nitrite will act as a base when it reacts with water. And again, at this point, before you even picked it up, you should know in this type of titration at the equivalence point, that's a hydrolysis type deal. So again, you should kind of know where you're going before you do the calculation here based on the type of calculation and based on where you're at. Obviously, the next reaction will be our NO2 minus. It will react with water. Again, it's going to act as a base, and logic tells us it doesn't have a hydrogen, so it can't give it away. So we're going to get HNO2 where it came from, which is what we always get, and we will get OH minus. Again, just from this reaction alone, we should already know our pH should be basic. We also should know that we need a Kb value in this case. And in this case, we have a Ka value. Any questions on that reaction there? All right, so as we talked about, this is sort of a continuation type problem. We're going to use our equilibrium from the first table as our initial concentration for the second. So this is going to be 0.05 molar. This is going to be 0 and 0. Change will be minus x plus x plus x. That is going to get us 0.05 minus x, x and x. And as I mentioned before, this is a Ka, I'm sorry, this is a Kb. This is a Kb because we have hydroxide on our product side. And this would be HNO2, OH minus, and NO2 minus. This means we need to convert our Ka value that was given to us into a Kb value. So that is where our Kw equals Ka times Kb. And in this case, Kb would equal 1 times 10 to the minus 14, which is the value of Kw, divided by our Ka value that was given to us of 4.5 to the minus 4. And that's going to give us 2.2 to the minus 11 as our proper Kb value. So as we talked about, I think earlier as well, the idea here is you might not be able to find the Kb value on the table, but since this is being produced in this reaction, you can find the Ka value on a table, and that's why we use that value to figure out the Kb value here. So we need to put our stuff into that expression. So I'll flip a page here. That means that we will end up with x squared, getting old, 0.05 minus x equals our Kb value, 2.2 times 10 to the minus 11. Here we could assume x is equal to 0. That's going to give us x squared 0.05 equals 2.2 times 10 to the minus 11. We're going to multiply the 0.05 to the other side. We're going to take a square root of it, and we will end up with an x value of 0.00000. That's a lot of zeros. 1054. Make sure I didn't miss any zeros there. Maybe use a little scientific notation, might be good. Let's go with 1.05 times 10 to the minus 6, hopefully. I think I got the right zeros. 1, 2, 3, 4, 5, 6. Yeah. We do want to check it since we did make an assumption here. So we're going to check it by taking our x value, and we're going to divide it by 0.05 and times it by 100, and we're nowhere near 1%. It's like 0.002%. So our assumption here is good, and because our assumption is good, a reminder that what we are seeing in terms of the x value is not the H plus concentration. It is the OH minus concentration. That means that this number here equals our OH minus concentration. And that means that we could then get the POH minus the log of the OH minus, going to be minus the log of 1.05 times 10 to the minus 6. And that will get us like a 598. Now, again, here, sometimes a lot is going on when you're doing these calculations. You got a lot on your mind. So perhaps if you looked at this value and you thought it was the pH, again, understanding that you're at the equivalence point in this titration, it should be basic. So again, if by some chance you thought this was the pH, it should not make sense to you. And hopefully you'll be able to recognize what you did there. So to get our pH, we do need to subtract it. So our pH here would be 14 minus 5.98, and that's going to get us an 8.02 pH, which does make sense because, again, we would expect it to be basic at this point in the titration, and then obviously a pH of 8.02 is definitely basic. Question on that part of the calculation? Okay, so let's see here where we're at. We have now done to the equivalence point here. And again, hopefully you can also see that each of these steps here are individual sort of calculations. Again, we're not continuing on with the volume. So when you have a titration problem, like we talked about earlier, we just kind of assume for each problem is separate, that you open up the burette, you close the burette, and added that volume. So lastly here, we want to look at D, which is 105 milliliters added. So D is 105 milliliters of our 0.1 molar sodium hydroxide added to our 100 milliliters of our HNO2, which is 0.1 molar as well. So again, here we're going to start with our reaction and our ice table. So our nitrous acid plus our sodium hydroxide, giving us some water, a little sodium nitrite. Much like everything else we've been doing, we're going to get our moles of everybody because we're adding volume. So our nitrous acid hasn't really changed. So it is still our 0.01 moles. Again, here using moles on this first table because we're adding volume. And our base is 0.0105 moles. Now, if you want to know where you are at in this titration, we just did the equivalence point and it was 100 milliliters. So clearly at 105 milliliters, we are past the equivalence point. Also, you could use your ice table to figure that out. We have more moles of what we're adding than moles of what we're starting. So again, that will tell you you are past the equivalence point. That is important for what we talked about because now what happens is we are just opening up that burette and dropping that base in. That means that our acid becomes the limiting reagent and our base becomes the excess reagent. And it means that the limiting reagent will be our change part here. So minus 0.01, minus 0.01, and plus 0.01. And that means at equilibrium, we would expect all of our acid to be used up. In terms of our base, we will have 0.000 moles and 0.1 moles of this guy. At this point here, our total volume, so we can convert back. We started with 100, we added 105. That is 205 milliliters. That means we want to divide each of these guys by 0.205 liters, again, to get it into molarity. And if we do that, we end up with 0.00244 molar. And for our other guy, we end up with 0.0488 molar. So at this point, what we want to do is figure out, what should we be doing? I will say that you already should know what you'd be doing at this point in the titration, but let me hopefully verify it for you. We have sodium hydroxide left over. We have sodium nitrite left over. Those two things are not related to each other. So you should not be using the Henderson-Hasselbach equation here, which people commonly do because they see two numbers and they say, that sounds good. Let's do that. So again, here we want to think about what we got going on. We have here a basic salt that will go through hydrolysis like we talked about in the last part of the problem. And we also have a very strong base. So by knowing that we are past the equivalence point, we do know that at this point in the titration, we ignore the contribution of the salt that's going through hydrolysis. And we know that the strong base is going to be the major contributor to the pH. And that means that this number here, which is our hydroxide concentration, is our OH minus concentration. And that means that the POH minus the log of 0.00244 gives us a 2.61. Again, if you mistakenly thought that this number here was your pH, it should not make sense because it should be basic at this point. The pH at this point should be 14 minus 2.61. And that is an 1139, which is definitely basic and what we would kind of expect at this point in the titration, since we are basically dumping base in there, right? We basically opened up the burette and we're just dropping in our sodium hydroxide. And that should add a lot of OH minus to the solution very quickly. That should cause the H plus concentration to go down. And in turn, that should cause the pH to go up. Question on that part of it? Question on any part of this titration or titrations in general? You obviously need to be able to, like I said, recognize those three titration curves, be able to calculate the pH anywhere along the curve, multiple places as well. Any question on what's going on here with these calculations? Again, the best piece of advice I could tell you is this. The good news is, it may not seem like good news, but the good news is all of these calculations that we have just done in the titrations, they are essentially all the calculations that we have already done. The key and where people have a lot of trouble with is knowing when to apply that calculation correctly. So that's why I really do stress that, you know, it's important to know where you are in the titration curve, because again, by knowing sort of where you are, like we saw here, like on before the equivalence point, I know I should end up with a buffer. That puts you on the right path in terms of your calculation. It also gets you in your head what you should expect to see in your calculation. And that hopefully can sort of ward off any problems that may come about, especially if you're like, hey, I should end up with a buffer, but I didn't, right? So these are things it's really important, not just to be able to do the calculations, but to be able to know what you're going and where you're going. Yeah, it makes it a lot easier if you kind of know where you're going versus I'll just get in the car and drive. I don't need directions, right? I'll eventually find my way there, and you might eventually find your way there, but you might hit a lot of wrong turns along the way. So that's why it's really important to have that conceptual understanding of what's going on and where you are, so that you know literally in all these titration problems, you should literally know what the pH should be. Should it be acidic, basic, or neutral? You should also kind of really know what type of calculation you should be doing before you pick up that pen to actually do the calculation. Any questions on any of that? Okay, so we might as well finish up this chapter. I think we have one last little thing to talk about, which is acids and bases and indicators. So let's talk about that. So indicators, as I mentioned before, indicators are really sort of like weak acids, and they have a protonated form, which is here. That's what the H is. So this is like H plus, and IN is a generic term for an indicator. And they do break apart into this sort of like weak acid equilibrium. And depending on sort of the ratio of the protonated indicator to the deprotonated indicator, if it is greater than or equal to sort of 10, we will typically see the acid color of that indicator. If it is less than 10, we typically will see the base color of that indicator. So indicators, as I mentioned, do work over a specific pH range. And over that pH range, they actually do change color. So for example, like I mentioned before, the very popular one, which is phenolphthalein. It's a fun one to spell, P-H-T, I think, H-A-L. So phenolphthalein, again, is a very popular sort of indicator that's used a lot. And it works over a pH range of 8.3, as I mentioned earlier, to about 10. Again, on this 8.3 range is kind of colorless. And then it gradually, like I said, goes from a kind of a super light, you can barely see the pink color, to a very, very dark pink color there. And you can kind of see it. It is right here, I think, on this slide. So at about 8.3, not so much color, kind of a tinge of pink and darker pink as you continue down the path there. And that is why, for example, when you typically have done a titration, maybe in Chem 50, maybe Chem 40, I think they still do titrations. A lot of times that you do a titration of vinegar, and vinegar is basically acetic acid. And you do a titration of like vinegar and sodium hydroxide. So when you think about this combination here, that is a weak acid and a strong base. And from our conversation of a weak acid and a strong base titration, you should know that at the equivalence point, we would expect the pH of that solution to be basic. And that is because, as we just saw in those examples, when we reach the equivalence point, we will end up with a salt. And that salt will go through hydrolysis and produce hydroxide. So for example, the one we just did was right there. This was the pH that we got when we reached the equivalence point in that last example, 8.02. It's basic because, again, we have that combination of a weak acid and strong base that's going to generate that salt that will go through hydrolysis and produce that hydroxide. So something like phenolphthalein works pretty good for that because it works over specifically that pH range of 8.3 to 10. And that is why they tell you when you do that titration, as I mentioned earlier, that you need to stop your titration when you first see the first hint of pink. And that is because really at 8.3 is colorless. And then it gets that really light pink. And if you stop your titration when you see that very first pink color, that will put your volume right around the equivalence point where it should be. Now, if you blew right past the equivalence point, not by one drop like I was talking about earlier or anything like that, but if you blew way past it, it'll put your stoppage over here at a pH of 10, which might mean that you have actually went, way over here, and you'd be very, very dark. Now, if you did it by just one drop, you may still be a pH of 10, but you might be over here, which is still, again, around the equivalence point volume. So that's what we were talking about a little bit earlier, that they usually tell you to stop when you hit that lightest shade of pink because that should put you right at the equivalence point. When you see that color change, basically the equivalence point is technically probably at colorless. But as soon as you're visually able to see that change of color to the lightest shade of pink, that means you should be like right there at the equivalence point or pretty darn close to it. Also, why what I talked about earlier, that you could technically, as we talked about with the equivalence point, because it goes vertical, only add 1 or 2 drops past the equivalence point, and you may actually see it go really dark pink. And you may still be okay in that case because you may actually just be like right here, which again is that same volume. But as I talked about earlier, if you opened it up and went way past the equivalence point, you may actually find yourself over here. But at some point, there's kind of no distinction in the color that you see. At that point, it's pretty dark pink all the way through here. and you can't really have a visual representation of you're near the equivalence point. But when you approach the equivalence point and it's kind of colorless here, and then you get that really light pink, you can feel confident that you're probably pretty close to where the equivalence point is. So that's why when we pick an indicator, there's a couple of factors that you want to think about when you pick an indicator. First off, you want to pick an indicator that will actually change color near your equivalence point so that you have that visual representation that, hey, you should shut your burette off and stop your titration. So for example, if in this titration we've been talking about, this guy right here, if I grab that guy right there, which is crystal violet, by the time I get to my equivalence point, it's pretty much just going to be blue, right? Because it's going to turn blue way at a pH down here. And if my equivalence point is way over here, I'm definitely not going to see any type of color change that's going to help me go, I should stop at that point. So there's really two sort of factors when choosing a good indicator. One, it should actually change colors near your equivalence point. And B, it does need to be able to do that exact thing. Actually, you need to be able to see that color change for you to stop your titration. So, something like phenolphthalein, where it's good for something that is a basic pH at the equivalence point, it might not be so great for something that is acidic at the equivalence point. You would want to use a different indicator. So up here on this table here, some different indicators, sort of the colors that they are in the acidic solution and basic solution, and the pH at which they kind of go across. Question on that. So why don't you take a second and choose which one you think would be good for this titration based on the list that we got going on the bottom. And while we're at it, why don't you try, let's take a look at, we didn't do that, did we? Let's say, what would be a good indicator for the NH3 and HCl titration? All right. So pick the one that would be good for the nitrous acid and KOH, and pick one that would be good for one or more maybe on this list here that would be good for the other titration. Okay, so let's take a look here. So we'll start with the combination of HNO2 and KOH. So again, HNO2 is a weak acid and a strong base titration. So as we were just talking about, a weak acid, strong base titration, we would expect that when we reach the equivalence point, because we're going to generate that salt will be a basic salt. So we would expect a basic pH at the equivalence point. That means that these are some indicators. And again, in acidic solution, for example, thymol blue is red, and then it turns yellow when it gets to basic, and so forth as you go through the list here. Now, because it's basic, we have a few options here. These three at the bottom might be good, but I would say probably your best choice would be the last two only. So you may ask, why is, only, was that creosol red and our good friend phenolphthalein be a good choice? Why wouldn't perhaps bromothymol blue not be a good choice? So if we look at bromothymol blue, it works at a pH range of 6 to 7.6, which means if you sort of think about the colors that you'll see, in a pH of 6, it's probably going to be yellow at this range, and then it's going to go blue. And since our pH at the equivalence point is going to be basic's above 7, which means it's really not going to change color until around here, which means it's going to probably still be blue. When it would change color, perhaps, it would be back in this area. And at that point, you actually are not near your equivalence point, right? You probably are still maybe a little bit far from the equivalence point. So although this guy does get into the basic range, we might not be able to clearly see the color change when we actually need it. So although it is, again, a little bit into the basic range, it is not enough into the basic range to probably be effective, as opposed to like our creosol red, which is 7.2 to, was that 8.8? That's a good little run of color change that's going to occur in that basic range, right where we might need it. And then obviously our phenolphthalein running a color change from 8.3 to 10. Again, we're going to probably be able to see the change in color to help us stop the titration. And that's the purpose of the indicator, is to help you stop the titration correctly. Again, with something like the bromothymol blue, there's just not enough in that range to allow us to physically see the color change and know we should stop. Question on that there. Now, I added the other one, which is our Nh3 and Hcl titration. And this is a weak base and a strong acid, which means when we reach the equivalence point, like we talked about in this type of titration, we again should have a salt that's formed. But the difference is that salt is going to be acidic. So we would expect our pH to be acidic. And that is, like what we had here on, we can just take a look here. Yes. Go look at their example here. And we can see at the equivalence point, we're shooting at something like 5.28 in this specific titration here. And that is definitely acidic, like we saw earlier. And what that means is, and we'll just use that number as sort of an example here. Our pH at the equivalence point, I forget what it was, we'll go with 2.8, something like 5.28. So what we would want to do is look for a indicator that will change color within that range. So probably on this choice, if we go with that as our sort of theoretical pH, probably something in this range would be really good. Again, it covers that range. We probably can see the color as it's going to change. And be able to sort of witness that change when we do our titration, and again, be able to witness that color change occur when we do our titration there. And so, for example, methyl red is yellow, and then it becomes orange. Right? So we would be able to see that change in methyl red going from a yellow color to probably just that hint of red, or orangey type color, and we would know we should stop our titration at that point. Again, something like this, for example, even though it's acidic, may be a little too far outside of the range for us to actually see the color change. By the time that thing would change color, we would be way too low in terms of our pH. So again, even if it's acidic, the sort of indicator, it may not be appropriate, the range for which it works over for your particular titration. A very good way to pick if you have like the choice of any indicator you wanted on the shelf, you would probably, if you were going to do a titration, calculate what the theoretical pH should be at the equivalence point, and then kind of choose an appropriate indicator based on that theoretical pH. Question on indicators or how to choose a proper indicator. Question on titrations at all, or anything we've been talking about today? Okay. So that should wrap up this chapter. This chapter had a lot of stuff in it. And again, this is why this chapter and the next one gives people a very hard time. There is a lot going on in these chapters. A reminder that on Tuesday we will have a quiz, and it is on this chapter. And I believe we cut it off at, buffers, if I'm not mistaken. So I think we cut it off at buffers from this chapter. So it'll be everything possible in this chapter through buffers, which is good because, you know, the exam is coming up, I think, in a couple weeks. So that should help you. So we will lecture on Tuesday, and I think we'll take the quiz maybe at the beginning of lab. And then after the quiz, we'll come together and talk about the buffer experiment that we will start on Tuesday of next week. A reminder that you have part 1, I think, of the hydrolysis is due today. Part 2 is due on Tuesday. So make sure you are working through those things and get those things turned in on time and not too late that you miss your opportunity to turn it in. Any questions on any of that stuff that we've been talking about today or what's going on next week? Okay. So thank you very much for listening. I'm sorry it turned into like a double. Do you have a question? Somebody know?
Professor?
Yeah.
For like, I know this is a lab, but will you upload the lecture?
Yeah. I'll upload this one. I'll get it up there. I'm gonna have to cut it up a little bit so we don't have like that hour of blank space. But I'll put it up there with the lecture from this morning. Other questions?
For the Ka, Kb values, some of the values aren't in the text. Where do we find it?
You'll have to find it in the. You'll have to find it in the text or some other reliable source. But just a reminder about that, I'm assuming for the hydrolysis reaction we're talking about, our experiment. So for example, let me see if I can find a page I can scribble on while we have this up here. For example, I think that's empty. Yeah. Okay. Let's just say, for example, one of your salts was NH4 plus, and it's going to go through a hydrolysis reaction, right? So the hydrolysis reaction it will go through, like we talked about, is NH4 plus some water, going to make NH3 and OH minus, right? So it's going to basically, sorry, go this way. I'm sorry, I wrote that wrong. Let's try it again. Take 2. All right. So since this is a acid, because it comes from a base, it's going to donate its H plus, and we will make that an H3O plus. So technically, this would be our hydrolysis reaction, which how they term it as KH in the book or the lab, and you would do this reaction here. And technically, this is a Ka value. because of it producing H3O plus. Now, the problem that I think what a lot of you are asking or might be asking is I can't find perhaps, say, this guy on a table for a Ka. You might be right. But if you look at a Kb table, you will be able to find NH3. And that is where that guy came from. And if you look at the NH3 reaction, it would technically be NH3, which is a weak base, plus water, gives you NH4 plus and OH minus. I'll just jump in the gun there. This is a Kb expression. And this Kb value, which is like 1.8 times 10 to the minus 5, when you could find it on the table. So you can find this value on the table, although you might not be able to find a Ka value for that. And this is the correct value that you should use with Kw equals Ka times Kb, where our Ka value would be Kw divided by Kb. And in my example here, 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5, which you can find on the table. And if you do that, you will get a value of 5.6 times 10 to the minus 10. This value here is the Ka value for this reaction, or the hydrolysis K value. And that is where you should find it. So you may not be able to find some of your salts on a table, but you need to find where they came from. And how you do that is what we talked about earlier as well, I think, when we were talking about this, is this NH4 plus comes from NH3. So I could actually find NH3 on a table, but it is the Kb, which means I need to reverse it. And you know it's the right thing because when I write the NH3 reaction, look at what I produced, NH4 plus, which is this guy. So my recommendation would be write the correct hydrolysis reaction, and whatever it produces, which is where it comes from, you should be able to find that on a table. It may be on a Ka table, it may be on a Kb table, and you may have to use Kw to convert it into the right value for Ka or Kb. So you might not be able to open up a table and find the actual Ka or Kb value for your hydrolysis reaction, but you should be able to find where it came from on a Ka table or a Kb table, and then do the appropriate calculation to figure it out. So in our example here, the value here would be 5.6 times 10 to the minus 10. Question on that?
Thank you.
You're welcome. Other questions? Okay. All right. So let's see here. Like I said, quiz next week, lecture quiz. We'll start the buffer experiment next week. Reminder, you got those parts of the hydrolysis that are due. No type report for that. Again, just whatever each of those assignments were in the modules, what you need to upload. Other than that, thank you again for listening to what turned into a double lecture here. I will cut this one up and put it up online with our lecture from earlier so you have it. And other than that, I think I'm good. If you're good, if you still have questions, I'll be happy.